already.
All right. Nevan.
To start, the color of halogens. Sorry, what? So did you say something, sir?
I didn't say anything.
Oh, okay, sorry. The color of halogens darkens going down the group. First, fluorine is pale yellow, chlorine is green yellow, bromine is orange brown, and iodine when solid is gray black. However, it is a purple vapor. Number two, melting and boiling points. They increase down the group because of the increase in van der Waals forces. Their number of electrons increase due to their increasing size. So more induced dipoles are going to form, which is what van der Waals is. Hence, there is an increase in bonding between atoms and increase in melting and boiling points. Number three, volatility. It decreases down the group because there is an increase in van der Waals bonding between the atoms. Hence, fluorine is gas, chlorine is gas, bromine is liquid, and iodine is solid in room temperature.
The trend of reactivity down the group. Reactivity decreases down group 17. The reason why is because there's an increase in shells, which causes more shielding effect, and the longer distance between electron and nucleus, which outweighs the increasing positive nuclear charge, thus making it harder to accept electrons. What is electronegativity? Electronegativity is the ability of an atom's nucleus to attract a bonding pair of electrons. As you go down the group, there's an increase in number of shells, which causes an increase in radius size. Sorry. So the outer shell is much further from the nucleus, which causes the shielding, which increases the shielding effect and causes attraction between positive nuclear charge to be weaker, as there is shielding, making it harder to attract electrons. Thus, all these points together causes electronegativity to decrease down the group.
For number 6, the more reactive element can displace the less reactive element. As explained in number 4, reactivity decreases down the group. Bromine is more reactive than iodide, and thus will displace iodide in a sodium iodide solution. Halogens dissolve well in cyclohexane, and the resulting colorization is indicative of the halogen used. In this example, the newly formed iodine molecules will form a top purple layer of cyclohexane. For number 7, group 17 reactions with hydrogen become less reactive than the group. Fluorine reacts vigorously in a dark and cool environment. Fluorine is explosive when not exposed to sunlight. Bromine will react slowly even when heating. And iodine is even slower, to the point where an equilibrium mixture will be formed. Number 8. By stable, it means that you need the more heat you need to break it down. As explained on number 2, melting and boiling points decrease on the group. So HF is the most thermally stable in group 17. In conclusion, thermal stability of hydrogen halides decreases down the group. This is because as the molecule size increases, bond length will increase, and as a result, less energy is needed to break the bonds.
To test for halide ions, we can dissolve them in dilute nitric acid and silver nitrate. A silver insoluble precipitate will be formed, and its color will depend on which the element was tested. Silver chloride will turn white, silver bromide will turn cream, and silver iodide will be yellow. Fluorine does not form a precipitate, and we should use a fume cupboard when testing for halide ions, as toxic nitrogen oxides are released. Silver chloride will dissolve in both dilute and concentrated ammonia solution, while silver bromide only dissolves in dilute ammonia, and silver iodide does not dissolve in ammonia at all.
All right, for number 10, the So for number 10, as you can see here, sodium chloride reacts with H2SO4 to form NaH2SO4 plus HCl2. So while this reaction is used to produce this mentioned salt, the reaction cannot prepare HBr and HI. Because even though they will be produced, there will be a further reaction in which the HBr and HI will decompose / oxidize. This is because the H2SO4 is such a strong oxidation agent, thus causing this reaction. However, it must be noted that H2SO4 is not strong enough to oxidize HCl2. Next, so as mentioned above, here are, well, I said that the HBr and HI can be formed by reacting NaI and NaBr with H2SO4. The following reactions will occur. So for bromine, H2HBr will further react with H2SO4 to produce bromine gas and sulfur dioxide. The reddish brown Br2 will be a reddish brown gas, while SO2 will be toxic fumes. And for HBI, hydrogen iodide, they will further decompose to form iodine gas, sulfur dioxide, and H2S. And here are the following if you want to read that. While these three above will be products of HI being reduced, the sulfur will appear as a sulfur yellow solid. Hydrogen sulfide will smell strongly of rotten eggs, and iodine is produced as a purple/violet vapor. Because of the mixture of gases produced, this method is not recommended for producing HI, and neither is it for HBr.
When chlorine and sodium hydroxide are mixed, a disproportionate reaction occurs, in which a disproportionate reaction will cause an element to both oxidize and reduce. For example, when Cl2 is reacted in cold alkali, in this case 15 degrees Celsius of sodium hydroxide, it will form a sodium chloride salt, sodium oxide, and water. The oxidation in sodium chloride, Na will have +1, and in sodium oxide, Na would have +2. Chlorine in hot alkali, which requires a temperature of 70 degrees Celsius, chlorine will react with sodium hydroxide to form sodium chloride salt, sodium chlorate, and water. We will obtain sodium chlorate in this reaction instead of sodium oxide, and the chloride ions will have the oxidation change from in -1 for sodium chloride and +1 in sodium chlorate.